does Ty look okay with this shirt? My wife said it wasn't okay, but then my daughter said that it was okay. What do y'all think? Y'all, you don't care. Okay. Usually take my daughter over my wife. All right. Let's see. I just want to remind you that we have an exam. Today is the 15th. So we have an exam coming up on the 6th. So we have another week or so, but it's not that far away, and that's going to cover, chapter 0.5. I think we call it 1.5. The chapter on flux and fields and all that business. So you'll see some of that again. And then also, hopefully you've already done all that homework and you mastered all that business. All of chapter 2, and then maybe even a little bit of chapter 3. Chapter 3 is like a one-day chapter. We just define current, we define resistance, and then we're done to move on to chapter 4. All right, so it might cover quite a bit of material. I just want to make sure that you got that in your mind as you're moving forward, that you're keeping up with what we're doing. I know that all of y'all are, right? Yes? Okay, this next test is going to have a lot of material. Some of it's going to be kind of difficult. Let's try a clicker question we left off with last time. This one, when you're finding the potential. Remember, when we found the potential, we did a little simple example of multiple point charges. I just add up, I calculate the potential due to each individual point charge. If I have one that's negative, I have to include the negative in that calculation because it creates a negative potential. And so let's try this. I want to know what is the potential up at the top of this triangle right here due to these charges, and then also recognize that 2Q is actually 4 microcoulombs because Q is equal to 2 microcoulombs. So a 4 and a negative 8 microcoulomb charge on this triangle create what type of potential at this point? And also, while you're doing it, I want to point out that as with the electric fields, we don't have to have a charge right here to have a potential. We could have a charge right here, and there would still be a potential there due to these two charges, but I don't have to have a charge. I can still have a potential at that point. So it defines the potential in space, not because there's a charge there. All right, let's try to wrap it up in about 15 seconds. I'm going to stop soon. I do want to just point out, some of you have probably recognized this, that I have a positive double, I have one charge that's half another charge, and they're both equidistant. I could just say, well, half of this charge cancels out half of this charge, and so my total potential will really just be negative 2Q at a distance from 1 meter. So I'm going to stop this at 255, and then I'll show you what I mean. Okay, awesome. Let's see, A is right. Let's see, what lies at the bottom of the ocean and twitches? Have I told you this? Now, what lies at the bottom of the ocean and twitches? A nervous wreck. That's not very good, is it? You do like it? Okay. All right. So to do this, the total potential is the sum of all the individual potentials. That's going to be the potential due to the 2Q plus the potential due to the minus 4Q. So that's going to be K times 4 times 10 to the minus 6 coulombs divided by 1 meter plus K times negative 8 times 10 to the minus 6 coulombs. I have to change that to coulombs. Divided by 1 meter. And so that gives me negative 36,000 volts. Notice, as I said before, that this one is twice this one, so I could just get rid of this and make this negative 4. Like you can simplify that a little bit. All right, we'll come back to this. Let's do a few clicker questions. I don't think we've done any of these, so you can find these in the back of your workbook. Am I right that we haven't done any of these? Okay, let's try this one. Proton and electron are in a constant electric field. You release the proton from the positive side and the electron from the negative side. Which feels the larger electric force? Alright, let's stop in about 10 seconds. Stop in at 45. 45, just guess if you're not sure. Okay, good. They feel the same magnitude force but the opposite direction. You can think about it a couple different ways. Probably the easiest way is to say, well, F is equal to Q times E. And so since Q is the same for the electron and the proton, then they're going to feel the same force. They have the same charge and the same electric field, but the electron feels the force in this direction, the proton feels it in the opposite direction. Sort of going back to what we saw before, but fields and potentials are related, so they'll sort of have some intermingling of them. All right, which of them, same situation, which of them feels the larger acceleration? Proton, electron, the same or neither, or opposite directions? Same magnitude, but opposite directions. All right, we'll stop at 30 seconds. Okay, why does the electron feel the larger acceleration? Like 10,000 times smaller. It's much, much smaller. You're right. So the electron is a whole lot smaller, so you thump it and it just goes a lot farther away. It accelerates at a much faster rate. Isn't it 10,000? It's like 10 to the minus 27 and 10 to the minus 31. Yeah, that's like 10,000 times smaller. All right. Which one, when it strikes the opposite plate, has more kinetic energy? All right, let's stop at 35. 35. Okay, yeah, we're all over the board here. So we want to think about this in terms of energy and maybe potential or work. A couple different ways you could think about this. We could say that the work is equal to QE, that's the force, times the distance, delta x. Now, this is the work done by the electric field, and whatever work is done by the electric field is imparted in energy to the particle. Q, well, Q is the same for both the proton and the electron. E, that's constant, it's the same for both. They both experience the same. And delta X is also the same. So the electric field is going to exert the same force over the same distance, and so it does the same work on both particles. So it imparts the same work, imparts the same energy. We can also think of our basic idea of potential, that is energy per charge. The potential is the energy per charge, and since they cross the same potential, when they go from one plate to the other, they both experience this potential difference of VBA, that is the difference in potential between these two spots. And so if they experience the same potential, they have the same charge, they're going to gain the same amount of energy. So both acquire the same amount of energy. Good job, the three of you. It seems like it should be the electron, right? Because it goes a lot faster. Or you might say, well, maybe it seems like it should be the proton because it's a lot more massive. It is true that they will be traveling at different speeds, but the electron, which is a lot less massive, will travel faster. The proton, which is a lot more massive, will travel slower, to the effect that they both have the same kinetic energy. Potentials are pretty important in helping us understand how particles move around. All right, we'll come back to this. I want to do a derivation. Not entirely sure where this derivation is going to fit on your exam next time. I'm not going to make you do the derivation on exams. I'm generally sort of moving away from that. But I might give you a similar but different derivation to do as a take-home. So you know, last time it was basically you just copied from the homework, I think, most of you. All of you, I think, maybe, right? Is that what y'all did? That's sort of what I expected. But I might give you a similar but different derivation where you have to follow the same steps, but, you know, for a different scenario. My point is just sort of make sure that you take note of how we're doing this. So here I have a charged object. This is just a bar. It's a bar that has charges distributed along it. We can describe how the charges are distributed along it based upon the linear charge density. Remember we talked about this before, how when we talk about densities, either mass or charge density, we can have linear density. That would be like charge per unit length, which we'll use here. You can have surface density, like charge per unit area, like we had on the exam. You had that sigma, right? Yeah. Or you can have volume density, which is sort of what we do usually. But here you need a linear density because we're talking about something that's long and narrow. I want to just point out a couple things here that I want to create a differential element. It'll have length dx. It'll have a position d, so the distance from here to here will be d, or excuse me, not d, x. This distance right here is d, and then I'm going to call this distance r. Now, if I have a charge right here, it creates a potential at this point equal to kq over r. Whatever that charge is times k divided by this distance r. But as I move along here, that r changes. It changes with the value x. And so what I need to do is to set up an integral in some way that expresses r in terms of x. And we can do that because, you know, trigonometry. And integrate from x equals 0 all the way out to x equals L. All right, so that's what we're going to do. We have this differential element. As I move the differential element along this bar, r changes. And because r changes, the potential at point P, due to my little bitty charge, my itty bitty charge, that's your differential element, the potential due to that itty bitty charge will change because the distance changes. And so we need to express r in terms of x, and then we'll integrate. So we start with our basic idea that our potential is the integral of dv you know, we're thinking in our minds, oh, this is really just the sum of the potentials due to my little itty-bitty charges. All right, an integral is just a sum. And this is going to be equal to the integral of k dq divided by r, where dq is the charge of my differential element. Now, I can describe dq in terms of lambda. dq is equal to lambda times dx. And so now I've transformed my integral. When I put this in, I can transform it into being with respect to a variable that changes, a variable that will go from x equals 0 all the way out to x equals L. Further, since r changes, I need to express it in terms of x and d, and r is equal to the square root of d squared plus x squared. So those are two substitutions that I'll need to make into this for dq and r, so I can express them in a way that shows that they change as x changes. Yeah, with me okay? Sort of? All right. Now when I put those in, I get an integral that I can do. It is the integral of k lambda dx, all right, that's my dq, divided by the square root of d squared plus x squared. Now some of these are constants. In fact, everything but x is a constant. K doesn't change. Lambda doesn't change. That's set for this bar, how my charges are distributed. And d doesn't change. That's just the point above the bar where my point P is. So everything there is a constant except for x. You ever use integration tables? No. You can look online. You can look, just, search integration tables. If you want to come by my office, if I give you this derivation, you can borrow mine. They make some handbooks that are really nice. I use the Schaum, like if you are going into graduate school, you might want to purchase Schaum's mathematical handbook. You ever heard of that? Man, when I was an undergrad, that was like my Bible. I carried it around all the time. And it's like it helped me in all my upper level classes. Anytime I had any sort of funky calculus or any funky area or volume or any of that jazz, it helped me to figure out how to do integrals, how to do different derivatives, all that jazz. So anyway, they have online integration tables. And if you look there, you can find that the form of this integral looks like this. They give this integral. They say that the integral of du divided by the square root of u squared plus a squared, this was just straight from the integration table, that this is equal to the natural log of u plus the square root of u squared plus a squared. I think you can do this. I don't even remember how to do this, but you can do this integral. You do it by parts or something. You'll do this integral in Calc 2. You can do it by hand, but if you look in your integration tables, you can find the answers there. And this gives the form. Notice I take my k lambda out, so I have du as dx, u is x, a is d, because that's a constant. And then it gives me the form for this integral. And so then if I apply that, I get an expression for v, and it is k lambda, because that comes out, times the natural log of x, that's my u, plus the square root of x squared plus d squared. A is d. A is a constant in that integration table entry. And then I have to integrate it, or I have to apply my limits of integration from x equals 0 to x equal L. And what I get is this final expression, k lambda natural log of L plus the square root of L squared plus D squared. So that's the answer. The tricky part here is right up here at the top. It's figuring out how to express dq in terms of x and how to express r in terms of x. But once you realize that you need to do that, express your dq in terms of lambda, and you use Pythagorean theorem to express R. Okay? So, probably I'll give you a similar but different derivation that you'll need to do as a take-home for the next exam. I'll have to think about it. We have some time before that comes up. Okay? Just make sure that you have note of this on how it works. I think it might be in the homework too, and so if you're uncertain about it, you can look back at that. Okie dokie? I'm going to try to pick one that you can't find online so that, it's not just an exercise of finding it online. I like this. Y'all like this? Integrating over surfaces? When I learned this in calculus, I was like, we didn't do the whole mind-blowing thing back then because that's sort of a new thing, but. All right. Okay, let's look at electric potential energy. That's going to be closely related to electric potential. So remember, we said that the potential at point P due to this charge, I already said this is KQ1 over R. Now what we're going to do is we're going to think about if I have another charge over here, Q2. It's at a position of R equal to infinity from that point P. And since it's at that position, what is the voltage at this point where Q2 is? It's really, really far away from that point P and that other charge. So what is the voltage at this point over here? Is 0, right? Because as R goes to infinity, then the voltage due to Q1 is equal to 0 over at that point. So we imagine that we have this charge that's really, really far away. And what we're going to do is we're going to take this charge and we're going to move it. And as we move it, the forces that are acting on it slowly get bigger and bigger and bigger and bigger. And we're going to put it right here. And we're going to ask ourselves, what amount of work did we do to bring this charge over here? And we ask ourselves that because it tells us what is the potential energy of this configuration of charges. How much energy, when I have these charges that are configured in this way, what energy is contained in that configuration of charges? And that's a pretty important thing to know if you're working with configurations of charges, molecules and the like. So how much energy, potential energy, is actually combined or contained within that configuration? All right? So remember that our voltage is energy per charge. So if I want to know the change in potential energy, it's going to be equal to Q2 times the change in potential, which is going to be equal to Q2 times V1 minus 0. This is my initial state. That is R equal to infinity, so V equal to 0. And then this is my final position at P. So up at this point P right here, my potential is equal to V1, that KQ1 over R. So that's my change in potential energy. So I can rewrite this as my change in potential energy will equal to KQ1 Q2 over R. Because remember, V1 here is equal to KQ1 over R. So I get this expression for the potential energy of two charges. And let's just sort of recap what we've had, because we have sort of a lot of things that look alike. We have forces. We've already seen forces, so you won't see them again on the next exam, but you can see them on the final. We have forces as KQQ over R squared. This is a vector, by the way. We have electric field was KQ over R squared. That's also a vector. Now we're getting into scalars. We had potential, which is KQ over R. And now we have potential energy, which is KQQ over R. Those all look really similar, and they look similar for a reason, because they're all related. In fact, they all go back to this force. right? The force is what causes the field, or rather the field describes the force. The potential is related to the energy, which goes back to that force. Because when I have two charges together like that, they have the potential for motion because there are forces acting on them. As you let them go, they fly apart, or they combine together. All right? Okay, so with our scalar quantities, we need to include our signs. That if I have a negative charge, it has a negative potential. If I have a negative charge and a positive charge together, they have a negative potential energy. You understand what that means? That if I have a positive charge and a negative charge, if I let them go, they're going to suck together. So in order to hold them in that position, I actually have to do work on them. So I say that they have a negative potential energy because I have to hold them back from going into one another. Now, if Q1 and Q2 are both positive, the potential energy is positive. That's what I meant here, that you include the signs. So if those values for Q1 and Q2 are positive, the potential energy is positive, and then work must be done to hold them in place. In fact, positive work has to be done to hold them in place. All right, there's a slightly different way to think of this, but you get the same result. I'm going to show you this, but let me just point this out, that our work is equal to Q times delta V. This sort of goes back to our definition of what is voltage, but work is equal to Q times delta V. So if I think about moving this charge, the amount of work required to move it over to point P is equal to Q times delta V. That's kind of a good thing because you were probably thinking that as I was talking about, well, I have this charge over here and I'm moving it, the force gradually increases, but I have to continue doing work to put it over here. You were probably thinking, oh gosh, we're going to have to do another integral, right? Because I have this force that varies with position, right? That's what y'all are thinking? No, you're not thinking. What are you thinking it? Well, you can do that, but it's very difficult to do that, to integrate as I move this charge into position. That's not that difficult. You could do it. But it's a lot easier to think about the potential and how the potential changes. That the work is just equal to the charge times the change in potential. Y'all don't look nearly as excited as you should be about this concept. It kind of is fundamental in how you think about charges and the potential energy that's contained within those charges. We'll look at some problems. Oh, so if Q1 and Q2 are opposite in charge, the potential energy is negative. I've already said this, that you have to do negative work must be done to hold them in place. So in that case, the applied force is in this direction, but the displacement would be in this direction. Whereas over here, the applied force has to be in that direction, and the displacement is also in that direction. So that's positive work, and that's negative work. That's not terribly important. The point is just remember that when you're calculating potential energy, you include the signs. So if I have one negative charge, I have a negative potential energy. If I have two positive charges, I have a positive potential energy. If I have two negative charges, I have a positive potential energy. All right? Include your signs, just like you do with potential. Let's see. Let's go back up. I want to show you something. No, let's go to this page. I just want to show you how to calculate the potential energy, and then we'll go back to the previous page. So let's say that I want to just know the potential energy of these two charges in this configuration. I would say PE is KQQ over R. That's 9 times 10 to the 9th. Q is 2 times 10 to the minus 6 coulombs. Negative 3 times 10 to the minus 6 coulombs divided by the distance, which is 1 meter. And so that's what, don't know what that is. It's 18 times 3, 54 times 10 to the third, negative 3. So negative 0.054 volts. Is that right? 18 times 3 is 54. Yeah, that's right. Right, so it's not volts either, I'm sorry, it's joules. It's a measure of energy, not energy per charge. All right. I want to go back to the previous page. I want to show you something. Sometimes, and you'll likely, we did this actually. We did this with masses. Remember with masses, we calculated the potential energy. We said that U was G(m)(m) over R, and we gave you a configuration of 3 masses. You'll see a very similar thing here. If I have a configuration of 3 charges, what I do is I find the potential energy of one set of charges, the potential energy of another set of charges, and the potential energy of the third set of charges. And then the total potential energy is the sum of those 3 potential energies. They just add up like scalars, so you just add up the values. If some of them are negative, you add them up as negative. If some of them are positive, you add them up as positive. If you got a bunch of charges, then you just add up all the potential energies. Alrighty? Let's try a question where you do that on the next page. So here I'm asking how much work is required to assemble the charges, but that's the same question as asking what is the potential energy. So whatever the work required to assemble them is the same as the potential energy. Remember, you're going to have 3 things. You want to break them up into your 3 distinct groups of charges. If we have 3 charges, we have 3 distinct groups. Feel free to share your answer. We'll wrap it up in about 10 or 15 seconds. Stop at 225. 225. Just guess if you're not sure. Very good. All right, so we want to take each configuration of charges. So here, I'm just going to do one of them, and then I'll point out the other 2. I say PE is 9 times 10 to the 9th. Q is 1, so that's going to be 1 coulomb times 2 coulombs divided by R, which is 2. That cancels there, and I'm left with 9 times 10 to the 9th. And then I do similarly for this one, and I'll get what, 18 times 10 to the 9th? And then I do this one. Am I right that I got 18 times 10 to the 9th? And this one I get 36 times 10 to the 9th? Yeah, 36. And then I add up all three of those. I add up the three potential energies, so it's 27, 57, 63. A is what you'll put? Yeah, so that adds up to be 6.3 times 10 to the 10. Just like what we did with the masses, except now instead of using the GMM over R, we're using KQQ over R. Alrighty? Alright. I'm going to tell y'all a little story. Not even a story, really. I told my lab yesterday. But the other day I met a former student from many years ago, so none of y'all know this student. But met her in the grocery store, and you know, like sometimes when you meet a student out after they graduated, it's sort of, I don't even say uncomfortable, because most of the students that I hear from, they say, yeah, I've got this great job, or I'm in graduate school, I'm in medical school, I'm about done, or all this. But sometimes you meet a student and they're like, well, you know, I'm working at Western Sizzlin or whatever. And that's okay, like, it's okay to work at Western Sizzlin, but, you know, it's not really what we want y'all to go out and do. And this student, she was an okay student, BC student, not a great student, but a good student. And so I sort of asked that question, so what are you up to now? And it was a little uncomfortable because I didn't know. It's like, the student could be working, I don't know, at a car lot or something. Again, nothing wrong with that. That's fine work. But, and then she told me, well, I'm going to wrap up my PhD in pharmacology pretty soon. I'm like, wow, that's really cool. And I felt bad later after that because like in my heart, I doubted her or whatever. But the point is that, you know what? There's lots of opportunities for y'all to go out and to succeed in the field that you want to go to, even if you get a B in physics, right? Like she did, or maybe even a C. Do you feel encouraged? Is that encouraging? Not really. Anyway, let's move on to equal potential lines. We saw this in lab. Equal potential line is a line where the potential is equal. That's where it comes from. Along these lines, the change in potential is 0. Also, the work required to move a charge along an equal potential line is 0. I'm going to call it EP line. Remember, because voltage, or potential, is defined as an energy per charge. So if I have a line over which the voltage doesn't change, that means that the energy doesn't change. I might have showed y'all this, but I like to think of it as a mountain. And on a mountain, if I go around the mountain at the same height, the amount of work that I do in that is 0 because I'm not changing my gravitational potential energy. I'm just staying along at the same height. And so this would be like an equal potential line. In fact, I could draw all sorts of equal potential lines on this mountain. This is an equal potential line. This is an equal potential line. That's an equal potential line all up and down the mountain. Now, if I move in between equal potential lines, that requires me to do some work. But if I stay along an equal potential line, I do no work at all. And that's true for charges as well. And just remember our basic definition that a change in potential, VB minus VA, between two positions, that this is equal to my change in potential energy divided by Q. And so if I'm staying along the same line, I have no change in potential energy. The electric field is always perpendicular to the equal potential line. You might see a question like this in the exam. I'm not sure. You might just probably have a multiple choice question. So my equipotential lines will always run perpendicular to the field lines. So if I just have individual charges like this, notice that these lines are always perpendicular. Now we'll get into the math of this soon. They always run perpendicular. All right? It turns out that one's the derivative of the other, and we'll see that soon. But when you're drawing them, they'll always be perpendicular. And so if I have a more complicated configuration like this, the equipotential lines, they always run perpendicular to the field lines. Look like this. If they go down the middle, notice it's always perpendicular. I'm just looking to make sure that these lines are always perpendicular to the field line. It's sort of like a basketball court, right? And I can have other equipotential lines that come along. Anytime I take a charge and move it along this line, it moves without any work at all. I don't have to exert any force to move that charge. All right, let's try this clicker question. At what point or points is the potential at its greatest value? A, B, C, or D, or C and D? All right, ask your neighbor if you're uncertain. Remember, potential is KQ over R. These lines, well, never mind. Potential is KQ over R. I'm going to stop at 55. Okay, good. He is right. V is KQ over R. So I want to ask myself two things. One, where is V biggest? Well, I know if R gets small, V gets big. So it's going to be biggest closer in. This is an equal potential line. So these 2 points, which are equidistant from the charge, they have the same potential. Can I tell you all a joke without you running off and telling all the administration that I told you, because it's kind of offensive? Like, it's a little bit vulgar. Are y'all okay? But we're all adults here, right? We can deal with that for the sake of humor, right? All right. What did the blanket say when it fell off of the bed? Oh, sheet. Don't tell anybody that I said that. I could get in trouble. I didn't really say the word, right? It was like a word that sounded like it a little bit. If you know what I'm talking about? I'm winking at you now. You see that? My wife says that when I wink that it looks like my entire face is just sort of hunching all up. Not that cool. All right. One last thing for this section before we move into capacitance. And that is, how do we calculate the electric field from the potential? Because you should be asking yourself right about now, well, gosh, the electric field and the potential, they seem very related to one another. And so there must be a way that we can mathematically relate them. And you would be right if you're asking yourself that question. There is a way that we can relate them mathematically. Because it turns out that the greater the change in the potential, then the charge will experience a greater work due to the electric field. So the electric field is proportional in some way to how the potential changes. Let me write it in that way. Same thing. But the electric field is proportional to how much the potential changes. And you're probably thinking, oh, we're talking about rates of change of the potential, so that must have in some way to do with the derivative of something. And we're actually not talking about a rate of change in time, but a rate of change in space. That as we move through space, how does the potential change? Usually when we talk about rates, we're talking about changes in time, but here we're talking about changes in space. So when the potential changes a lot, the electric field is bigger. And that's what we see right here. The potential lines are close together, and so that means the potential is changing a lot in space, that is, so the electric field is bigger. But when they're further apart, like right here, potential is changing just a little. So the electric field is small. All right? So we can do a quick little derivation. We can say that the work is equal to the negative Q dV. That's sort of our definition of work. And work is also equal to F dot D. Don't worry about the derivation. I'm just sort of showing you. Some of you are interested in this. So if you can set these two equal, minus Q dV is equal to F dot D. F dot D is the same as F cosine theta ds, where ds is the differential element and the position, and this is equal to minus q dv. Further, I can say minus q dv is equal to the force, which is qe cosine theta ds. So here ds is just the differential element in the direction of the E field. And E cosine theta is a component of the electric field that's in the same direction as ds. Don't worry too much about this derivation. You're not really going to see it again. But this is where it's coming from. This relationship between the electric field and the potential. May I go down from here? So we get this expression for ES, just a general expression for ES, is that the electric field in the direction S, X, Y, or Z, that would be, is equal to the derivative dV, or del V, del S. This is the Greek letter del. No, I'm sorry, it's the lower, it's sort of a funky lowercase Greek letter delta. But we call it, when we have this, we call it del. And this is called a partial derivative. It means that I'm going to have this function that's dependent upon x, y, and z, but I'm only going to take the derivative with respect to one of the variables, either x, y, or z. It's called a partial derivative. You might get into it in differential equations a little bit, but if you go past differential equations, they have a whole course, which is even more magic than differential equations, where it deal with these partial derivatives. They work exactly the same as far as we're concerned as regular derivatives. You just set certain terms as constants. And so we get this EX is minus del V del X. EY is minus del V del Y. And EZ is minus del V del Z. And then our total electric field will be equal to EX in the I direction plus EY in the J direction plus EZ in the K direction. All right, so let's just say I give you a potential that's mapped out in space. This potential as a function of X, Y, and Z is equal to, I don't know, let's just make it 3x squared y z. So potential in space, 3x squared y z. the way I'd do this is I would say EX is equal to negative del x of this function, 3x squared yz. And what you're going to do is you're going to set everything else constant except for x. The partial derivative, I take the derivative only with respect to x. And I treat all the other variables as constant. So I say I'm going to let y and z be constant. So I can say that this is just negative 3yz del x of x squared. See, I can take those constants out of the derivative. And the derivative of x squared, what is that? Derivative of x squared with respect to x. We know that. What is 2x, right? 2x, so 2 to the 2 minus 1. So it's going to be negative, this derivative is 2x. So it's going to be negative 6xyz. And then you can do similar things with ey and ez. ey is going to be negative del y, 3x squared yz. Well, let's see. I take the 3x squared z out. What's the derivative of y? It's just equal to 1, so that's going to be it. And then what do you think would ez be? Y'all think about it for just a second. What's the z component of this electric field going to be? Right, it's going to be with negative 3x squared y. Because the derivative of z with respect to z, it's just 1. So it's going to be negative 3x squared y. So if I want to know the electric field in space, it's going to be equal to negative 6xyz in the I direction plus, minus negative 3x squared z in the j direction minus 3x squared y in the k direction. And so if I want to know the electric field at any position in space, I can just put in my x, y, z coordinates, and I get the electric field in I, j, k notation, that vector for the electric field. All right, we'll do an example like that. You'll certainly see one of these on the test. They're just derivatives, right? So don't be freaked out that they're partial derivatives. You're just taking the variables that you're not taking the derivative with respect to and just saying, okay, these are right numbers, and just pull them out of the derivative. We'll do an example next time, okay? And now have a good day. Then we'll move on to capacitors. You're going to love. Capacitors are awesome.